Thinking about going solar, but not sure whether it's worth it for your home? Well, before you get quotes, there are three things you need to know about going solar and one easy way. Thinking about going solar, but not sure.
Good afternoon, everyone. Thank you for joining us today. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Here with us today, we have Dr. Daniel Ye, a board-certified engineer and a professor of engineering at the University of South Florida. Today, Dr. Ye will be discussing reinventing the toilet for global sanitation. We'll learn all about the NEWgenerator resource recovery machine. Before we get started, I just want to mention that you'll be able to message your questions at the end of the presentation. Once the presentation's over, you'll be able to type your question into the attendee chat panel on the left-hand side of your screen. Okay, let's get started. Welcome, Dr. Ye. Thank you for joining us today, and we're ready when you are.
Okay, hi. Marissa, can you see me?
Yes, we can.
Okay, great. All right. So hello, everyone. Welcome to this webinar, and I want to thank the Academy for inviting me to give this talk today. So the topic of today's talk is the NEWgenerator, right? And this is a machine that we have developed at the University of South Florida over the past couple of decades. And the topic we're addressing is global sanitation. We're part of a movement to reinvent the toilet for this purpose. So let me start with a really high overview, right? Planetary overview. We have a number of challenges that are facing our planet today. And I think the audience is very familiar with all the water, sanitation, energy, and food challenges that we face. What I want to submit to you is that we need to address all of these issues, not in silos, but look at their nexus, try to address them simultaneously because they're very much interconnected, right? And I'll get more into that. So in terms of the topic of global sanitation, right, it's year 2022, and we still have a lot of issues related to sanitation worldwide. Depending on how you count it, billions of people around the planet still do not have adequate sanitation. And this ranges from not having any toilet facilities at all, or having really poor toilet facilities, such that people are practicing open defecation, to having some type of facility, but no wastewater treatment, which means wastewater goes into channels, goes out through open pipes into rivers and sometimes into people's backyards. So it's a big problem, and you might wonder why don't we just solve this with the technologies that we have right now? We're often faced with maybe two types of choices when we're looking at sanitation. Um, you know, Most people here in the United States are familiar with the centralized approach, where we have sewer systems connecting our households, businesses, toilets, collect all the wastewater through sewer system and send it to a centralized treatment system. And this was largely made possible through the Clean Water Act. We built a lot of infrastructure. And if you don't have this, then you're forced to either use some type of on-site system, such as septic tank, or if that's not possible due to soil conditions, oftentimes we use something like a pit latrine, right? So we're kind of looking at both of these options, but really not a whole lot of things in between. Well, neither option is perfect. In terms of the on-site systems such as pit latrines, they're often faced with high usage rates. The ability for the pit to dewater is largely depending on the soil. So if you have poor soil conditions, it fills up very fast, and of course, it's very vulnerable to flooding. If you have a flooding event, and we're seeing more of that now with climate change, the contents of the pit will just be distributed where you don't want them to be. And then you look at the centralized sewer system; those are very resource intensive to operate, and we have to build an extensive infrastructure of sewers. And in terms of sewers, this is not something that the world's going to be able to do. There's some projection out to the 2030s looking at sewer access around the world, and you see that many countries or many regions on this map are either in the red or the orange or even green. So they're just not going to be able to have the resources to build the sewers and also to operate and manage the sewer systems. So sewer systems are also vulnerable. And here is an example from Florida. I live in Tampa, Florida, and a few years ago we had a tropical storm come through, and you can see that in the weather map here, Tropical Storm Colin. And the city of St. Pete Beach actually tweeted this out, saying, "Hey, we have a sewer system emergency. Everyone, please stop using the sewer because the sewer is full." I don't know about you. I never think about the sewer as an appliance. It's very kind of surreal, right? The municipality is pleading with homeowners to stop using the sewer because the storm has inundated the sewer, and that's largely because of sanitary sewer overflows, infiltration, and inflow problems. So sewer systems are vulnerable, and they're not by no means perfect, and there's a lot of maintenance costs involved. And at the end of the pipe, we have a centralized wastewater treatment plant, often based on gravity settling. So this has issues related to large footprint, and gravity settling systems are just going to be land intensive. So this is not going to work where space is at a premium. For example, in slums, where you have very little space, a lot of crowding, high usage, and oftentimes slums are really unplanned. So it's very difficult to map infrastructure to go along with the very organic growth nature of slums. So if you want to provide sanitation in a slum environment, you're going to have to do process intensification, a lot of that, and also you need some type of very compact treatment system, something that would be game changing. And if you can pull that off, I think that would be transformative and disruptive. So what we're really looking for, right, to make this work, we want something that's transformative. It has to be effective. It has to work, first of all, but then also it needs to be reliable, right? It can't just work once or work for a month. It has to continue to work, and you have to know how to maintain the system. System has to be affordable. May not The end user may not be the one paying, but somehow the economic model needs to be worked out so that it's ultimately economically sustainable. And it would be nice if you actually provide an experience that's aspirational. In the same way that we enjoy a lot of household appliances or smartphones, you want to have a good experience going to the bathroom. So, namely, a flush toilet experience, if you will, right? Oftentimes, that's what we get to enjoy. Most places in the U.S. and we don't think twice about it, but many places in the world do not have flush toilets, and it's the experience is different. So to make that happen, right, here's the question: as the developing world is building their infrastructure, do they have to go down the same path that the developed countries went through, recognizing that sewer systems are not perfect, or can they somehow leapfrog these technologies in a way that cell towers leapfrog landlines in the continent of Africa, many places in Africa, and now we have a better technology that doesn't require landlines. So what we're really trying to do is fill the gap here, right? Something that's on site but works a lot better than pit latrines, but it doesn't have all the intensive infrastructure maintenance requirements as centralized sewer systems. So essentially a non-sewer sanitation system, a platform. And not only do we want to do treatment, we also want to do recovery, because wastewater is a valuable resource. You can recover water, energy, nutrients, number of things from it. So can we pull that off? So that gave inspiration to the NEWgenerator project, or the concept. Right, we envision a resource recovery machine that can recover nutrients, energy, and water on site. Hence the name NEWgenerator. And how it will work is that this will be a platform or a box, right? Something that you can insert near the point of generation, near the point of use. For example, provide a flush toilet possibility to something like a latrine system, or a porta potty. Um, and then you can recover the energy, you recover the water, excess water, you recover fertilizer, maybe for greenscaping, or even to grow crops. Right, the possibilities are endless. So to do this, the first thing we're thinking of was, well, this really has to be a very non-energy intensive system. If it requires a lot of energy, that's not going to work in many parts of the world, because of high energy costs, unreliable grid. So to make the process low energy, we decided to do anaerobic digestion, right? And this is something a lot of people are familiar with. Essentially, in anaerobic digestion, organic waste is broken down by anaerobic microbes, goes through the various stages of disintegration, um, hydrolysis, fermentation, ultimately, methanogenesis, so you can make biogas. The nutrients that are bound up in the organic matter are liberated, so you have inorganic ions of nutrients. And of course, you have water. The problem, though, with conventional anaerobic digestion is that all of this is kind of mixed together, and there's really no good way of doing separation. I mean, there's a limit to technology, the limit of technology in terms of the separation. Um, Pathogenic organisms and colloidal materials are not going to be separated for the most part. And also, if you overload the system, it's very easy to upset it. So, what can we do to improve on the anaerobic digestion process? One thing you can do is add a membrane to it, right? So that's a hybrid process. You're going to use a biological plus membrane filtration platform. So when you do this, essentially the exit of the bioreactor is covered by a membrane, which in this case is an ultrafiltration membrane, 0.03 microns. So that's smaller than bacteria and most viruses. So we get to keep everything in the bioreactor, right? The pathogenic organisms, we intercept them, and a lot of them die off in the reactor, or we concentrate them. And also the slow-growing anaerobic organisms are kept in the bioreactor. So we overcome some of the kinetic limitations and throughput limitations of conventional anaerobic treatment. And you can then combine this process, and this is an anaerobic membrane bioreactor. And this technology has shown itself to be quite robust and flexible. For example, it's not always the bioreactor that's doing the treatment. Every second, every minute, it's actually the membrane during the filtration, during the rejection. So the membrane provides an absolute barrier for a very high quality water right off the bat. And really, the biology is there for management of solids and residuals, right? So because of that, you can use an ANMBR to treat, gray water to black water to food waste. I mean, COD can range from 100 to tens of thousands of milligrams. So it's quite robust, and you can safely remove bacteria and viruses. It doesn't matter what the temperature is. Doesn't matter how active the microbes are. And most importantly, you can handle intermittent loading and shutdowns and dormancies, and have very fast restart. And these are all very important criteria when you're looking at on-site sanitation systems, because they're going to be used sort of in a non-steady state fashion. How is this, anaerobic MBR compared to the more conventional aerobic variety? Well, there's several advantages. One is the much lower biomass production, right? From your bioprocess class that the sludge yield for anaerobic systems is 8 to 10 times less than aerobic microbes. So automatically, there's a much lower desludging requirement, which is one of the pain points for on-site systems. There's no aeration requirement, so you don't have to aerate to keep the bugs alive, and it cuts down considerably on the energy requirement, which improves its reliability because you don't have to provide the energy. Essentially, it's a carbon redirection process. Rather than just oxidizing the carbon, becoming have it be emitted as CO2, we get to redirect it to methane and have the opportunity to capture that as an energy source. So, theoretically, we can go energy neutral or even positive with this process. Now, as we develop this technology, there are a couple of frameworks that guided us in the development. The first one is we were fortunate to participate in the National Science Foundation's ICOR or Innovation Core program. If you haven't had the opportunity to participate in ICOR, very much encourage you to do that. There's different ways to get involved. Either you have an NSF grant, you can just apply for ICOR, or many universities around the country have ICOR site programs that students can form teams and participate in. But what ICOR does is it helps researchers think all the way down the road in terms of what the customers, the end users want, right? A lot of times as researchers, we have assumptions about how our inventions or technologies could be used, and very often there's a mismatch between what people really want. So ICOR takes you through this customer discovery process. You actually talk to people, you find out what their pain points are, and this is really important. What is really bothering people? What do they wish could change? What do they really want, out of some improvement, right? And because whatever solution you provide, it has to solve that problem. You don't want there to be a mismatch. And also, you start to think about your technology, not in terms of features, but in terms of what value proposition do you bring to this relationship, with the end user. For example, you can make their life better, right? Somehow. Um, and the flush toilet is an example of a value proposition. Our technology can make a flush toilet happen, and it'll happen because of a number of features, right? For example, have a high throughput membrane or something. But the end user doesn't care about those things. All they care about is the fact that they get to have a flush toilet now, whereas before they didn't. The other framework that we use to guide our technology development is the technology readiness level framework, which was originally developed by NASA. And this is a good way to look at technology in terms of their maturity, or as it goes through different maturation levels. So it goes something like this. It goes from TRL 1 to 9. 1 would be like a real basic proof of concept. You have an idea, you want to just like test it out in a beaker, see if it even works, right? That's like really basic stuff. And then you start to kind of combine components together into a subsystem, and subsystems start to come together, and you start to kind of move up to TRL 3, and you're still operating within the lab, and maybe you're using some type of simulant, right? And by the time you get to TRL 5, it means you have a system working, but is working with a simulated environment. So, for example, treating simulated wastewater in a laboratory setting, right? So that would be a TRL 5. And then TRL 6 would be going to a relevant environment, right? Going, say, out of the lab, where actually you don't have to, but but what you're doing should be one step away from the actual environment. They're very, relevant setting. And then when you go to TRL 7, it would be an actual operational environment that you're putting your system in. So oftentimes when we're doing pilot testing at a wastewater treatment plant, that would be something, somewhere between like a 6 and a 7. And then 8 and 9 are really just, additional maturation. By the time you get to 9, the system has been, fully validated through a number of iterations, and it's really, in NASA's case, flight ready. But in the case of wastewater systems, I think at TRL 9 it would be ready for commercial deployment. So we kind of use this framework to guide our process. So we started with the initial ideas, and we built our laboratory systems. And this will be the TRL 5 system that I would describe a little bit. And here I list the funding sources. And then in the TRL 6 system, we went out of the lab to a septic tank. And then later on for TRL 7, we had the opportunity to go to India. And that was sort of the early phases of our technology development. So I'm gonna talk a little bit about our journey through TRLs 5 to 7. In TRL 5, this was an anaerobic membrane bioreactor that we had in the lab. It's not a new generator yet, but it's a platform that we're able to evaluate the core technology, the anaerobic MBR, and really get familiar working with it and understand how to overcome the limitations like membrane flux and how to consistently get high quality water. And you can see in this picture the membrane that we have is a tubular membrane, and and that in this particular case is a single tube tubular membrane anaerobic MBR system, and we're able to get the membrane from Pentarex, using our X-Flow membrane. So based on that, we had laboratory results, and we went on to a TRL 6 pilot scale system. So at this point, we're thinking, we need to advance towards building a machine, right? And what you saw before was a mishmash of wires and tubes. It was not a machine that you can deploy. So this one actually needs to be somehow packaged. Okay, so I went to Home Depot, bought a hardware closet for tools, and then we decided to package our bioreactor within that with some basic control system, and that's what you're kind of seeing here in that TRL system. And we need actual wastewater. So my kids at the time go to an environmental school in the Tampa Bay area called Learning Gate, and voila, they have a septic tank. So we went to the school and said, "Can we please have access to your septic tank?" And said, "Sure, knock yourself out." Um, so we put our TRL system right over the septic tank, pulled contents from the septic tank, treated it, and we decided to do more than just treat the wastewater, right? Because we had NSF funding involved. And of course, with NSF funding, you have to do a lot of education and outreach, for your broader impacts. So we said, why don't we just turn this whole thing into a demonstration platform? Right, so it was BRATS, the Biorecycling, Bioenergy Research and Training Station. So not only did we treat the wastewater, we demonstrated, reuse, repurposing the effluent for things like growing microalgae, and we set up a greenhouse where we grew different crops, and we developed a number of lesson plans that ultimately were picked up by Teach Engineering and at the University of Colorado. So we had a lot of fun doing that. And here you see two of the students, Jorge Calabria and George Dick, who are very much involved with the development of BRATS. So from there, we knew how to operate the system in the relevant environment, subject to all the temperature fluctuation issues that and also the actual wastewater fluctuations you come across. So when we went on to TRL 7, so by this point, oh yeah, I should mention that for our TRL 6, the work was funded by the Gates Foundation through a program called Grand Challenges Explorations. So that program is still ongoing. Essentially, it's $100,000. You submit a 2-page proposal, and if it's a really good 2 pages, you get $100,000. So first time I tried, didn't get it. Tried again, got it on the second try. So with that $100,000, that allowed us to do the TRL 6 system. So we had some promising results, and then later on got additional funding, through the Gates Foundation, also in partnership in the government of India, and said, let's build a system that you can deploy to India. And wow, okay, this is a huge step, right? We never built anything like this. So we start to envision what the NEWgenerator would look like. We started to draw things up on SketchUp and got really good at drawing things on SketchUp. I said, well, this needs to be decentralized on site. Yeah, I mean, these are the core requirements: has to safely sanitize waste, has to be modular, plug and play, operate off of renewable energy, has to be compact, autonomous. We cannot, have operators standing around all day long. It needs to, run itself. And really, we're out after resource recovery, so water recycling, energy harvesting, fertilizer recovery. And in terms of the renewable energy, of course, you can potentially harvest biogas and use that energy to run your system, by putting the biogas safe through another generator. We ran some numbers and decided that, because we really didn't know what type of waste we were going to run into and could be quite dilute, we could go through periods where no one's using the toilet. It just wasn't reliable enough for us to run the system off of biogas. So we decided to go with solar, which was going to be much more reliable. And we're very glad we did that. Okay, so on the TRL-7, this is an actual system that we deploy. So our SketchUp skills got better. This is what it looks like. And we deployed our system to Trivandrum, India, in the state of Kerala, in the southern part of India. So in India, we were partnered with a company called Erum Scientific. And, and when you're doing research, you can't do everything by yourself. So you have to look for partners. And this was a really good partnership in that Erum Scientific was started by a group of people who are in the IT business. They recognize that India has large sanitation issues, and one of the big problems is nobody likes to use the toilet because they get dirty and smelly, and nobody wants to use them. So maintenance was the big problem. And I said, well, what if we can automate the toilet cleaning, right? Because we're IT guys, we know how to do that. What if we can have an automated toilet that cleans itself? And then further, we can monitor the toilet remotely. And if there's a problem, we can then send somebody to check it out. So they did that. And these systems, were quite popular, sold very well. They started to sell them all throughout India. But then they ran into a pain point. And the pain point was, Indian-based sanitation systems are very water intensive. Because instead of using, say, toilet papers afterwards, I use water to clean up. And where's all that water going to come from? In in places in India that are water scarce, and with climate change, this is getting worse. So somehow they're going to have to recycle the water, but they didn't have a technology to do that. Well, we did. So our scheme was, let's team up with Erum. They can provide the front end toilet, the front end user interface, if you will. We'll provide the back end system. We'll treat their wastewater, and we'll return clean water back to flush the toilets. And along the way, we'll harvest some energy if we can. And we couldn't just do it with just the ANMBR, even though that's the core technology. So the anaerobic biodigester is coupled with the ultrafiltration membrane, and you have to disinfect the water still, one more time past that, at least one more time, to have multiple barriers. So we use this electrochlorination process that I'll describe a little more. And that was sort of the platform. Okay, and we decided to put this inside a mini container. We considered a number of different options to house the system. I even thought about buying like a phone booth to put it in, and ultimately came across these mini containers that actually the military uses. This particular one is a quad-con, which means it's a quarter of the size of a 20-foot container, and 4 of them actually can snap together to form a 20-foot container. So there's some kind of standardization, some modularity involved. So we, acquire a container and start to build our, bioreactors, tanks that got those delivered. And this was a start. What you're seeing there is the bioreactor. You have the membrane module, and you have our product water tank. And that was the beginning. Our membrane module was donated by Pentair. And these are really awesome, high-performing membranes. So we tested a lot of different membranes over the years, and Pentair's are really awesome because we're treating high solids in our system, and we want a system that wouldn't clog up easily. Right? There's fouling, there's membrane fouling, there's also membrane clogging. So it's important to be able to have proper distribution on the feed side, to the membranes. And these Pentair X-Flows did the job for us. So there's a constant recirculation loop of the contents from the bioreactor that goes to the membrane module. That's from feed to concentrate, and then you have a permeate pump that pulls out the permeate along the way. So here you see some of the students involved during that stage. Robert Baer, George Digg, owner Ocean, Peter Zidek, Jorge Calabria, they were the core members who did the India phase of the work. And we started to build. We built the solar panel. Of course, the put together battery pack, a control system. Things started to come together. Oh yeah, and this was literally we were building the plane as we were flying it because we didn't have the experience, but we got funded, and we got that, which means we're on the clock, and we have to deliver the system by a certain day. So we're essentially designing and building at the same time, and spend a lot of time in a conference room in front of the whiteboard, sketching things up and just trying them. And came to the part, said, well, how are we going to automate this thing? Um, all of us are like civil engineers, environmental engineers, knew very little about automation. One of the students says, there's this thing called Arduino. It's a microcomputer, microprocessor. Maybe we can use that. I know how to code it, but not well. So we went out to reach out to electrical engineering and found a student who was an Arduino whiz. So he helped us do the automation for the system, and we he built the whole system to run on an Arduino Mega. And here you see the more completed system, with the membrane module. What you see in the forefront there is the electrochlorination system. Essentially, you input table salt to make a brine solution, and electrochemically that gets turned into chlorine gas, which is then swept into the cell, becomes hypochlorous acid, and basically bleach. So bleach is made on demand as we need it. And that's important because it's very difficult to store bleach, and it's also not safe to store bleach. So all we have to store in our system is table salt, which makes things a lot easier and much more reliable. And what you're seeing there in that bag is not the final biogas storage bag, but is essentially a variable volume, for the headspace of the bioreactor. Okay, so we built a unit. We had to get it deployed before the end of the year. So I had to learn how to do shipping, but heavy freight shipping. Look at a number of different ways to ship. Decided actually air freight was actually competitive, and there are actually planes that are big enough to hold a container. So we went with UPS Heavy Air Freight, and they put it in one of their planes and shipped it to India. Of course, with our luck, we ran into historical flooding in Chennai, which basically inundated the entire city, and even airplanes were floating down the runways. It was so flooded. So our shipment got delayed in Europe, by a couple of weeks. It couldn't fly into India. So by the time it actually finally flew there, we're behind schedule. We're rushing to get it on site, trying to do all of this before Christmas. But then the truck showed up, and that was a very happy day when that truck carrying the unit actually showed up. So here's me in front of the truck, and the unit got delivered. It was about to get installed on site. So here's me, live tweeting the installation of the system. I was such a happy person. I had to change my travel, but I got to see the system get on site. So we got that installed. So the scheme at the site is to have two of these e-toilets, provide the front end interface. And by the way, this was installed at a school in Trivandrum. So the front end toilets will be these automated toilets. They'll generate the wastewater, go into a holding tank. We'll pump it up, treat it, recycle it back to the toilets for toilet flushing. And it was a big hit. The students love using it. But we also found out about all the ways that the system can break. For example, we even found like a T-shirt shoved down the drain pipe. So definitely learn a lot about reliability and maintenance requirements. We ran this entire operation for about a year, and the whole time was off of solar, and we're able to treat and recycle the water. And here's just a quick data on what that looks like in terms of turbidity incoming and exiting. This unit was near a sports field, which generated a lot of dust. It also gave us good experience on how to maintain a solar panel against dust coverage. We built a hydroponic system on the side of the unit for two reasons. One was that was our attempt to maybe do some nutrient management or nutrient recovery. The other is really for education and beautification, if you will, of the system. Well, it turned out to be problematic because the kids, especially younger kids, I'm talking about kindergarten, first grade, second graders, love to pick those plants out of the hydroponic system. So pretty much like the bottom 3 or 4 rows were just constantly being pulled out by the kids. So lesson learned, if there's anything really integral to the operation of the system, you cannot put it on the outside. It has to be inside of the container. Okay, and here's some pictures of the unit, with the control system, battery bank, and also on the wet side with the membrane module and the treatment unit. And here's another picture of the whole setup. So, this was a very nice project in a way that we really got to interact with the students, and it's just great seeing their happy faces. And this was right around Christmas, so there's some Christmas celebration. And one of my favorite pictures is this. Here's a child trying to prank his friends and keep him from getting trying to lock his friends inside the toilet. Of course, it didn't work. They just opened the door and they came right out. But anyway, so from India, we pivoted and went, got additional funding and went to Durban, South Africa. And what we're hoping to accomplish in Durban, South Africa was to treat a different type of wastewater. The school wastewater that we had in India was rather dilute, right? And that's largely because of two things. There's a lot of water use in the Indian type of sanitation. And also kids essentially went to school to pee, but not so much to poop. So our COD was quite low, just a few hundred. So we were able to handle that, but we really would like to have COD in the thousands or even tens of thousands. So, the Gates Foundation was setting up a platform, a technology demonstration platform in Durban, South Africa. So we went there. And Durban has some very interesting situation that's quite reflective of the rest of South Africa and probably many parts of the developing world. It's really just rapid, unplanned urban densification. So here you see essentially a factory that was built, right, and you see housing nearby. But as soon as the factory was built, people wanted to just basically move in and move close. So within a span of months, I mean, I'll go back a little bit. You can see the difference. People just moved in. Wherever there's land that you can put up a structure, people are living there. So this type of situation makes provision of infrastructure very challenging. These are essentially informal settlements, and the South African government has a commitment to provide water and sanitation to people wherever they live. Okay, but then if people decide to seemingly overnight live on a hillside, you have to figure out how you're going to run water and sewers to up the hill. So that was their pain point. How do we provide water and sanitation, especially solve our sewer problems? And in Durban, it would cost billions of dollars for them to properly sewer the entire city. So that was definitely a huge pain point. And water scarcity is another one. There was drought, and it would be good if they can cut down on water consumption. Um, these are the portable water, basically sanitation hygiene platforms that were used. Durban is a container port, so there's a lot of used containers, and these used containers were converted into basically facilities for toilets, urinals, hand wash, showers, and laundry. So, but the pain point again was they have to build sewers. So if we're able to bring in a new generator, connect with these community pollution blocks or cabs, we can maybe do this. Let's say the cab will generate 10,000 liters of wastewater a day. We will treat half of it, or actually treat all of it, but recycle half of it back for use as toilet flushing, right? And then that results in 5,000 liters of makeup water, and that will go to like the highest grade of water for human contact, hand wash and showers. But we would generate clean water, but not potable grade, so that could be used for toilet flushing. Now we get to save half the water, and we actually generate this additional stream of water that could potentially be used on site for irrigation. It would be clean and sanitized. So this is what the site looks like, and already there's a garden nearby, that people are using to grow some stuff. So here we go. We build NEWgenerator version 2. More experience, a little bit smarter, lessons learned, and we start to think about building a system a little bit differently, with a better control system. We also put in a nutrient management system internal to the container that I'll show a little bit. Part of what contributed to the success of the South African project was the fact that we knew we were going to have an engineer on site to help us run the system. We're able to bring him to USF while we're still building the unit. So he learned to basically not only operate but trouble the unit inside and out, and we're able to simulate a number of failure modes before the unit was even shipped out. This made all the difference because Lindelani was able to troubleshoot the unit on site, and he knew the system very well. So that was definitely a key to success. And here's our student team at the time. A number of people there. Let's see. You see Cynthia Castro in the foreground. She was doing the bioelectrical chemical system at the time. Later on, she was doing project management on the project. Robert Bear is in the background, and I'm hiding behind him in the container. So we built the system, and Robert was really excited. He wanted to get onto the plane as soon as he can. And we had help of facilities, move it to the loading dock, packed it up. It went into another UPS plane, and this time it got to Durban very quickly. And Durban has these really cool trucks that has the crane integrated, and those are really nifty because essentially you can carry anything and lift anything on site. Like, you don't need 2 trucks to do this. This is what our system looks like on site. There's Lindelani and another student, Siskelo, who is doing some project on horticulture. And our scheme was basically to treat the wastewater from the cab and then recycle it and be able to generate some clean water that's useful. So we have some guiding principles in terms of how we wanted the NEWgenerator to look like, to do, and we're able to sort of refine those and articulate those more as we went on, right? So kind of broke into 4 categories. The first one is that the unit has to be high performing, right? It has to be able to have high capacity, generate high quality effluent that's pathogen free and suitable for whatever reuse is needed. It has to be resilient and robust and be able to handle intermittent flows. Because if you don't do that, this is not a sanitation system. Okay, so I'll show you some data coming up. But here's the system from the 2 sides. You can see the bioreactor, the membrane module, the electric chlorination system, solar panels, battery bank, control system, all that. Okay, so here's our scheme for our setup in Durban. What's in that blue box there is the community pollution block. And we were very fortunate because, we had the opportunity to modify the community pollution block and separate out the different waste lines so that they all went into a valving chamber, and we're able to turn on and off the different types of wastewater that we wanted or didn't want. Anything that we didn't want to be included, it just got diverted to sewer. So essentially, we can pick and choose and generate with the wastewater that we wanted. And the wastewater then went through a bar screen, through an underground equalization tank, and then through our system with the major steps of anaerobic membrane bioreactor, nutrient capture system, electric chlorination, and the product water. And then water gets recycled back. We went through 3 stages of testing. First, with just black water from the toilets, which would be largely fecal material with some incidental urine in it. And then for stage B, we added in yellow water with urine, and then went back to black water later on for some additional qualification trials. Okay, so here's some data that I'm going to show, and these are all published, and I'll show you the citation reference in the next few slides. But I want to share with you the data. On the left, these are temporal plots, so you see like from October 2018 to February 2020, and on the right, these are spatial plots. So how the system behaved as it went through from influent to the reactor to membrane permeate to the nutrient capture system to the final product water, right? And you can see how, for example, in TSS, There's certain amount of TSS in the influent, and there's some accumulation in the bioreactor, but then solids are removed promptly by the membrane, and it goes through additional polishing in the steps further after that. COD follow similar profiles. So what's interesting about this technology is that things do get accumulated in the bioreactor, but if you can manage them and so that they don't interfere with the membrane operation, it doesn't matter what you have in a reactor. Your effluent quality is going to be really high. So then the question is, what happens to all the solids and COD that builds up in the system? Well, that's where the anaerobes come in to break them down. But you do see some accumulation over time. So we're using this buildup of solids to guide us in terms of figuring out, sludge wasting rates or desludging requirements in the system. And we actually went two whole years without wasting anything from the reactor, which, as you remember, is one of the pain points. Turbidity follows similar profiles, and as well as color, right? So these are important. Obviously, you want to generate, good-looking effluent. Now, nutrients are a little more interesting because anaerobic systems don't remove nutrients. They liberate nutrients, if you will. Converts organic nutrients to soluble inorganics. So you have to do something with it. Either you have to remove it, or you have to somehow capture it and repurpose it, reuse that. So we went with a nutrient capture system that was a combination of zeolite and activated carbon, and we wanted to test its capability. So the bed worked really well, as you can see in the initial period. Here's the influent nitrogen, and the effluent was always extremely low. Less, about 5 milligrams per liter or less. But then the bed got saturated, and you see the nutrients start to break through. So because this is a study, we wanted to basically be able to do mass balance. So we let the nutrients break through so that we can do those mass balance calculations. And then we started to do some regeneration events, essentially treating the bed with some brine solution to do on-site regeneration. So all of this was to basically give us knowledge about the extent of operational period for the bed, what are the regeneration frequencies, and how to regenerate in the field. So we have no problem removing nitrogen, but then it does incur a maintenance requirement. Phosphorus is a different story. The system wasn't designed so much to remove phosphorus at the time, but still we got some phosphorus removal. I'll show you the results and then in 2 slides. Actually, in the next slide. Yeah. So you see here, here are the effluent numbers. Now, one thing that we were doing in this field trial was, there was a new standard that was developed called ISO 3500 non-sewered sanitation system standard, basically to provide a guide, a roadmap for certification for this type of technology. And here you see all the different criteria, for effluent water quality, and also in terms of, water chemistry, and also in terms of pathogens. We were able to meet all of the water quality parameters except for phosphorus at the time. We're getting about 40% removal when the standard called for 80. But then subsequent to that trial, most recently we got data back. We've been able to hit over 80% removal on phosphorus. So and we're able to do that because of testing limitations. We're only able to test bacteria and helminth, but we were able to remove both of those. So the system is did pretty well, and we published the results in a couple of the papers that you see here. And then there's some additional publications that are coming out, especially related to the horticultural study. Okay, so the other category of features is the unit needs to be compact, right? We want to basically have process intensification. It needs to be a very compact, portable system with small footprint that's easy to install. And here you see some kind of time series photos of the unit being developed by that very nifty truck right into the informal settlement. It swung over somebody's house, actually, avoided telephone poles, and we're able to just basically get it right on site. So the whole installation from truck to the site was about half an hour. And then after that, we connected the plumbing, electricals, and we're off and running within a couple of days. Got the PV panels up. The next thing is that we envision that the unit needs to be simple to operate. It needs to be. You need to be able to basically start it up rapidly. We need to have autonomous operations, be able to control this with an app, and that's in fact how we design the system so that it's app enabled. We can track this remotely, and having those capabilities is important because here's a picture from George Sabanicus's textbook on water reuse, and basically I see the future as a combination of centralized and decentralized units are all working in concert, and maybe the centralized utility needs to be running all of this, and you need to have telemetry on all of these things. Otherwise, you're going to have just many points of failure. So you start to be able to form essentially water microgrids, to complement the centralized sewer system. Have options, and depending on the size of a unit, you can either have a one-to-one, one unit per house, or maybe if it's too much technology, you can have a cluster of homes that report to one unit of NEWgen and recycle water back. And this can solve problem not just in the developing world, but I think in many parts of the U.S. that about 40% of the U.S. is on-site wastewater treatment. We start to be able to form microgrids, uh, being able to not just let water escape into the ground, but recycle the water. Or if you know wastewater, or if the water just doesn't drain into the ground, like say in Lowndes County, Alabama, you can basically have a surface recycling system to deal with that. And finally, the system needs to be flexible. You need to be able to be used for a number of different applications. Basically working with different front ends, working with different end users and different applications. So we kind of envision that the system could be used in slum environments, informal settlements. That it could be used also for ecotourism to protect the very, for example, beaches that people go to see. Places like Hawaii, there's 80,000 cesspools in Hawaii, and that really shouldn't be the case. So tourism definitely creates problems in many places. Schools, parks, and also for emergency and humanitarian settings like refugee camps. Refugee camps are interesting because the host country often do not want to does not want to put down the permanent infrastructure, because then the camp will become a town. So they go with temporary facilities, but that often means for sanitation it's a hole in the ground, latrine type of application. So if you can containerize the technology, then you're technically a temporary solution, but yet it's a much more robust and high performing system than a hole in the ground. So I see for sustainable sanitation, we really need three things. One is that you need a technology that will do the job. You have to have protection. You have to have that intervention, that barrier, and break down the cycle of disease transmission. But going beyond that, the unit has to be affordable from a life cycle perspective. It can't just be cheap right off the bat. You have to think about the recurring operational costs. So it has to be affordable, but on a life cycle basis. And it would be nice if actually you provide some value proposition back. So having a treatment system that can generate recycled water and give people flush toilet that they didn't have before would be a nice value proposition. Okay, so throughout this past many years, there's been some nice highlights. One of them was, in 2014, we won the K Museum Prize. The group of students, we took first place, and that was a really nice validation of what we were doing at the time. That somebody thought what we're doing was a good idea, and they decided to give us the prize money. And then from there on, we've received other accolades. One of the ones we're most proud of is in 2020 received the Patents for Humanity award from the USPTO, saying that we basically applied our innovation towards something that will help humanity. But probably the highlight is this. Getting to meet Ronnie Chang, and did a segment on the Daily Show, a comedy segment, to talk about basically poop, and what Bill Gates and other people are doing about that. So that definitely was fun. But back to more serious stuff. We talked about going to TRL 7 and beyond. So working with the university's technology transfer office and working with the Gates Foundation, we've been able to commercialize the technology. We in addition, we continue to work with Yerum Scientific in India, and now they are licensing the technology. They're building units of NEWgenerator for many of their customers. And then also we've commercialized in South Africa as well, working with a company called WC Projects. And here you see last November, World Toilet Day, WC launched a system in a township near Soweto, provided basically a flush toilet platform that the folks there didn't have previously. And what WEC wants to do next is to provide a sanitation platform for a school in the Eastern Cape. And this is really challenging because that school, like many schools in South Africa, does not have electricity, does not have running water, and does not have sewers. So, which means either pit latrines or chemical toilets. And we're going to provide this platform. Essentially, the water is going to be harvested rainwater. We're trying to make the rainwater go as long as we can. So that's going to be a really challenging project. We've also been able to form a startup, and it's called BioRenew. And what we're trying to do with BioRenew is go after a lot of the needs here in the United States or in the Western Hemisphere. I mentioned Lowndes County, Alabama previously, but there are many similar needs in California and Texas and Appalachia, Indian reservations. So we're hoping to, help in that regard. Another highlight is being able to progress, and actually we're working with NASA now, because the anaerobic MBR technology is highly scalable. So we can go big, or we can go small. So NASA is moving on with the Artemis project to go back to the moon and eventually to Mars. And there needs to be technologies that can do a more sustainable recycle of water, but not just recycle the water, but also recycle the nutrients for plant production. So this is a unit that we built called the Organic Processor Assembly. It's basically a mini ANMBR system that treats wastewater for a crew of 4. And we're currently testing this with Kennedy Space Center. So I want to talk about BTS, not the Korean pop band, but behind the scene in terms of what it looks like behind our work and some of the successes that we had. Right. So the first thing, obviously, are the students. I think as a professor, there's nothing better than working with students who are just super motivated, bring different skill sets to the table, highly committed, and basically have this can-do attitude, that anything can happen. And it's really great to see their contribution and how they've grown over the years. And we have so many students involved in giving them the opportunity to travel internationally and be part of this project. Trying to list out all the names of the students and then all our partners in South Africa with the University of KwaZulu-Natal, who's basically working with us in Durban and Kanisa projects, providing field support. And there's just too many people to thank. But here are some of the core people currently working, to manage the project. You have Robert, Bear, Cynthia Castro, and Gary Shu, and of course Linda Lani, the prototype engineer. Give me a second here. Okay, so in terms of behind the scene, the second point is you need a support system. And so here's I'm trying to get into a little bit of career advice now. We have a lot of students on the call, and many of you are probably looking to go into academia. And I want to tell you, research has a cost, and it doesn't come without a cost. And you need to decide what kind of researcher you want to be. If you want to work on discovery, basic research, and not leave the lab a whole lot, that's definitely a very successful pathway. But then on the other hand, if you say, well, I really want to see my technology go into the field and even get commercialized, and in fact I want to address global problems, there's only one way to do that. You have to travel a lot internationally. And it's not just traveling to project sites as they're running, but years prior to that, you need to be traveling to meet people, have face-to-face, set up relationships, all of those things. And what's going on with the family while you're doing all that, right? So I've been very fortunate that my wife has been really supportive. But she works a full-time job, and she holding down the fort, raising our kids while I'm gone. So it's not easy, so you kind of have to decide what is the pathway that you want, and it takes a toll. And you know spending 16 hours on a plane and coach in the back of a plane is not fun. And also, I missed my son's birthday because the flight got delayed coming back. All those things, right? That's just a part of the what you sign up for. So need to kind of talk to people and have that thought out ahead of time. The second part of this support system is you got to have mentoring. You can't do things alone. I mean, you don't develop these things in a vacuum. I certainly didn't. So I have had some wonderful mentors over the years. Before I did my PhD, I worked with Byung Kim at Ford Motor Company, and he really, just provided a lot of guidance on, helped me actually get to Georgia Tech, working with my PhD advisor, Dr. Paulo Stathis. And Spiros basically taught me how to do anaerobic digestion, which then I carried on. But I knew how to do anaerobic digestion, but I've never worked with membranes, right? That didn't happen until I was doing my postdoc with Craig Criddle. And we had the opportunity to work on an MBR project with NSF-funded STC. And, here you see pictures of the MBR team. And, this was what kind of gave me the opportunity to start to work with membrane bioreactors. And I want to credit Craig with really, he came up with the idea of using MBRs for water reuse. And in fact, maybe some type of a water machine that can self-sustain. He had it on his website years ago. I wish I'd grab a copy of that. It's no longer there. But basically, like a self-sustaining water machine. Working with an MBR, anaerobic MBR running that. So, what we worked on then was really about mainstream wastewater treatment. We're trying to basically change how mainstream wastewater treated with an ANMBR followed by a BNR and MBR. And then before I came to USF to be a professor, I came across this article. This was the June 2004 issue of the Water Environment Technology from WEF. And it's an article about the outcome of the Bellagio framework. Basically, a group of 14 water wastewater experts got together, did a retreat in Bellagio, Italy. I'm sure they drank a lot of wine, but they also came up with some heavy hitting ideas. They outlined the anaerobic MBR, whether its attributes are successful, but what it still needs work on in terms of being able to fill that gap, fill the need for global sanitation. Basically cost and affordability, chemical usage, ease of operational use, and institutional acceptance, all of those things. So, so I was starting to be, just got my gig to be an assistant professor at USF, and looked at this, why don't I try to address these things? So basically this became my roadmap for the NEWgenerator for the next, 15 years. I mentioned the 14 water wastewater experts and I knew there were a lot of big names. I didn't know everybody, and what I didn't realize until much later is that one of my collaborators in South Africa, Chris Buckley, was one of the authors on here. So we worked with Chris Buckley through the University of KwaZulu-Natal in South Africa, and Chris is, if you know him, he's very well known in the field of sanitation. I mean, very well known and respected. So it was really because of him that we were able to actually do the project in South Africa. And then I didn't realize he was one of the authors on this article. So at some point it dawned, it kind of came full circle, and Chris and I were like, wow, okay. So, he spent some time in Bellagio, came up with some ideas with other people and just planted the seed. And then somebody else came along and, working with them made it possible. Unfortunately, we lost Chris very, recently, a few months ago. And so it was a huge loss. I think this is a void that can never be filled because he has a unique combination of not only being technically savvy, but also has just superb interpersonal skills and networking skills, and everybody knows him and everybody respected him. I mean, it's very difficult to find a person like Chris Buckley. So, Chris, thank you for everything that you've done for us, and we miss you. So with that, that concludes my talk on the NEWgenerator. Happy if you want to reach out to me, happy to discuss with you more or send you the publications I mentioned. And I'm going to turn it back to Marissa.
Excellent. Thank you so much, Dr. Ye. Now we'll take a few minutes to answer some questions. If you have a question, just type it in on the left-hand side of your screen where it says attendee chat, and we'll answer them as they come in. I did see a few questions also up top where the speech bubble icon is. So there's questions coming in 2 locations. You can just go, you can just look at them and answer as you go. You see them, or do you need me to read any?
No, I'm seeing them. I guess did that audio problem get resolved? I guess it did. Right about 10 minutes.
2 people had an issue, and we were going to send them the recording.
Okay, yeah. How are non-digested solids handled? So we basically try not to have non-digested solids come into the system. We know that there's trash that's not going to get digested. You basically have 2 ways of dealing with it. One is that you can grind it up and let it come into the system, but that increases your inert fraction, and you have to then desludge more frequently. The other is to screen it out and keep the trash from coming in. But that basically creates a maintenance issue of further upstream, and that you have to keep your screen clean. Right now, having said that, there's always going to be non-digested solids. For example, we recently emptied our reactor and found out that after 4 years of operation, there are tons of seeds in there. So basically, seed from the people's waste, and then end up being accumulated in the reactor. Capital operational cost for the system, it really depends. We're trying to make this competitive as an option, in the way that NBRs are competitive with conventional wastewater treatment now. So, of course, it's going to cost more upfront than, say, a pit latrine, but pit latrines have really high operational costs. So the fact that you're getting more in return, and also, for example, we're projecting 10-year lifetime on the membrane, 15 years on the system, and the membrane can go a whole year without cleaning. So really, we're trying to minimize the operational costs to basically have a competitive life cycle cost. Estimated cost of residential unit in the U.S. Has it been sanitary issues or homelessness in the U.S.? It depends. Again, we've looked at some costs for example, on-site systems, ATUs, and I think we can have a system that's competitive with that, with the those on-site treatment units. Homelessness, I think that's going to be site specific, because it's not just about the treatment system; it's about having clean toilet facilities that are accessible to people. Once that can be provided, then yeah, we can be anywhere to provide the waste. Can 100% of the material be sourced in South Africa or in Africa to construct a complete system? Yes, absolutely. Yeah, so that's, the systems don't have to be built locally. I mean, not every component, but you want to make sure that the supply chain works. So with the global commerce, things are being moved around the world, but you want to make sure that most of the components can be sourced locally, and for the cost reduction. So what we're doing is working with our commercial partners is optimizing the system for local context, and also localizing it, with local materials. So I want to ask if you're still working on any current waste treatment for developing countries. Also have opportunity to accept new graduate students. Yes. Please reach out to me directly, and we can talk. If you're interested in graduate school. Siskelo, good to see you. Are there any plans to test the suitability of recovered nutrient produced grain crops such as maize? Well, Siskelo did a number of greens, including Swiss chard. I'm going to turn that question back to you in terms of producing maize. What would you like to do? Is the plan to always get the membrane donated? No. when you first start and you have very limited funding, you're trying to stretch everything out. Asking for donations goes a long way. Everybody wants to help universities, but of course, the sustainable plan is that people have to make money on all the parts, right? But what you're hoping to do is to be able to address that through volume purchase. If we make one, we're buying one part, of course, the cost is going to be, one way. But if we buy 1,000 or 10,000, now you're getting to volume pricing. So membranes are actually not the most expensive part of the system. Have you been in conversation with regulators and communities in Cape Cod? No, I have not. They have a huge problem with nutrients from septic tanks. I'm aware of that. Okay, well, I'd love to talk to people up in Cape Cod. Yeah, I know in Florida, it's, big issues with on-site wastewater treatment, high water table, not having sufficient vadose zone for nitrification and so forth. So which is why regulators have asked a lot of systems to go to on-site or above ground ATUs, aerobic treatment units. So I think our systems could be a replacement for the ATUs. How often is the membrane cleaned? Okay. We've gone a whole year without cleaning, but we think probably a more sustainable plan is to clean it maybe every half a year, along with other maintenance that you have to do to the system. So first, I want to say this is a machine, right? And all machines need to be maintained. And a great example is your car. You have to change your oil. You have to change your air filter. You have to change your oil filter. You have to put air in your tire. Otherwise, a small problem will become a big problem. Same thing with this. We have to do scheduled preventive maintenance on the system, and if we can do that, we can head off, things breaking abruptly without warning. So this is one reason we did the field trial to figure out what is, for example, like the mean time to failure between different things, or mean time to maintenance, between items. So membrane cleaning, we can do that, within a couple of hours on site. So while it's being cleaned, you could be doing other things. Technician can do that. It's basically clean with a light bleach solution, and the recommendation now is to do it half a year. The rest of the time, the whole membrane operation is automated. Some comment on the membrane. We're not trying to push for high flux. Oftentimes for municipal or industrial systems, you see people pushing really high flux. That's fine if you have the resources and oversight to basically keep an eye on it, to be able to clean it when it starts to foul. But we're putting these systems in places that are going to be neglected, and we have to think about running a marathon, not a sprint. So we designed the system to be able to run at a lower flux at a cost of maybe a little more membrane material, but that gets folded into the whole capital cost of the system. And also the whole filtration, backwash process is all automated. Could this be applied with container-based sanitation or other semi-centralized systems where waste is collected elsewhere from the user interface, or would it make more sense to keep the technology in the same neighborhood as the user? I think it would work. If you collect waste from elsewhere and to run into the system, I see one of the reasons we put this in a container is to demonstrate that it can be moved anywhere and also can be scaled. So you can either communicate directly with the front end toilet, or waste could be brought in from elsewhere. I'll give you an example. One of the realms that the Gates Foundation is working on is fecal sludge management. So not so much wastewater, but fecal sludge. So basically, when you empty the pit latrines, the contents have to be taken somewhere. And right now, there's no uniform process for treating fecal sludge worldwide. Well, now there is, because the international standard ISO 31800 came out. But that fecal sludge treatment oftentimes works in concert with wastewater treatment. So something like the NEWgenerator a larger one can handle the wastewater in concert with some type of a physical chemical system that treats the solids, for example.
Excellent. Thank you so much, everyone, for all your questions. And thank you, Dr. Ye, for sharing your knowledge with us today. If anyone has any additional questions, please feel free to email Dr. Ye directly or email me and I can put you in touch. I actually put his email address in the attendee chat as well. Our next webinar will take place on Wednesday, June 15th at noon Eastern. This webinar is titled Logan Township Water Reclamation Facility Expansion and will be presented by Richard Chikansky, who is a board-certified engineer and a senior associate at Remington and Vernon Engineers. You can go to aaees.org and go to our events page to register. And just a reminder, if you're not yet an AAES member and you're considering joining the Academy, please email me to discuss our membership options. My email is mwaterman@aaees.org. We'll have a recording of this event up on our website by tomorrow, and I'll be sending out PDH certificates this week. That's all for today. Thank you so much, and everyone have a great day.
Thanks, everyone.
Bye-bye.